All right, this is our second pulley sample. They seem to be getting exponentially more difficult. If you need to stop and pause this video and figure out what I've done, by all means, I don't feel like you need to watch it from start to finish. So here we are again with a simple pulley, part 2 on page 490. Now, instead of having just a force pulling down on this rope, we actually have a block. And so we want to consider how fast that block is going to move. We've got a couple of things that we need to write down, although we're not getting any numbers for this, okay? The mass of the pulley, we're going to use M sub P for the mass of the pulley. That's going to come into play when we try to determine its rotational inertia. We're going to have the mass of the block, right? We're going to use that in our Newton's second law formulas. And that's really, I guess we also need the radius of the pulley in order to determine, again, rotational inertia. Now, I put a sub P there, although it's the only radius that we need to deal with, but let's just get used to being explicit about what we're actually doing. So what's our toolbox for this kind of problem? We've got one thing that's rotating, that's the pulley, and one thing that's moving in a linear fashion, that is the block. So we can unpack our entire toolbox here. We can say the sum of our torques is equal to the moment of inertia of the pulley times alpha. Okay, that's our rotational Newton's second law. We can also say the sum of the forces acting on the block is equal to the mass of the block times the acceleration of the block. Now, it's only the block that's doing the accelerating, but we can put a sub there as well. The other thing that we need to realize, because we're going to use this to bridge these two situations, is our translation from rotational to linear motion. So we've got V equals R omega, and we've got A equals R alpha. And we can substitute those as we see fit. Okay, so let's start with what we have. Let me draw the pulley here. Here's the R, and here is let's just call this the tension force. Okay, so what is the sum of torques on the pulley is going to equal I times alpha. Well, the only torque that there is the torque from the tension in the rope. So we have R times Ft and then sine theta, but this is a right angle, so it's 1, so it's just R times Ft. Okay, well that's equal to the moment of inertia of the pulley times alpha. Now for the pulley, the moment of inertia is 1/2 the mass of the pulley times the radius of the pulley squared. And then we've got our alpha there. So if you want to have I'll cross that. So we have R, and then we have Ft. Now, there is only one R, and I know I've got it capitalized in one place and lowercase in another place. I apologize for that. Let's solve this for the tension in the rope. Because for this problem, there's only one rope. The block is pulling on it and it's rotating the pulley, so that there's only one tension. So believe me, this is the easier of the problems we're going to do. So the tension force then is 1/2 and mass of the pulley times the radius of the pulley, because I have 2 here and 1 here, and so 1 canceled out, times alpha. Okay, so I've solved for the tension in the rope in terms of some other stuff. Now, if you remember from our Atwood machine problems back in Unit 2, tension in our rope was sort of the bridge between the two blocks, and it's going to work the same way here. It's going to be our bridge in between the pulley and the block. So here's my first expression for tension. Now I'm going to draw a free body diagram of the block, and this one is really pretty easy. Down is MB times G, and up is the tension in the rope. Now I'm assuming that the block is going to pull down because there's no friction in the pulley there. So positive is going to be down. So we have the sum of all the forces on the block is equal to the mass of the block times the acceleration. Well, MBG, right, the weight of the block is going down. tension, is acting up. So down minus up equals MA. All right, so that's all this was. This is back from unit 2, down minus up equals MA. So I'm going to then rearrange this formula for FT, and I'm going to get, after some rearranging, MBG minus MBA. Whoops, that should be A. Okay, so what have I got here for all of my troubles? I've got 2 expressions for the tension in the rope, so I can set them equal to each other. So that's what I'm going to do. I'm going to go to the next page because it gets messy. All right, so my first expression for tension, 1/2 mass of the pulley, radius of the pulley, times alpha. That's right here. I'm going to transfer that. I wish I could copy and paste. There probably is a way. MP, RP, alpha, and that's going to equal my other expression for tension, which is MBG minus MBA. Okay, so I can't remember if I even wrote this down at the beginning of the problem. The 3 things we're looking for is alpha, the linear acceleration, and the tension. So what I have here is I have one formula, but I have 2 unknowns, right? I have acceleration and angular acceleration. So, but remember, I have my conversion factor, if you will, right? The linear acceleration is alpha times the radius. So I'm going to say, well, alpha is equal to A over R, and I'm going to substitute that into this guy, all right? It's messy, but we can do it. It's just algebra. MP, RP, but now my alpha is A over R. All right, so you can see something's going to cancel there, equals MBG minus MBA. Now, just FYI, I'm not factoring that mass out because I want to solve for acceleration, so it wouldn't do me any good at this point. So here go my radiuses. Okay, what do I have here? 1/2 the mass of the pulley times acceleration equals the mass of the block times G minus the mass of the block times A. So let's get our A's together because that's what I'm solving for. 1/2 MPA, bring the other one over, plus MBA, and then leave the MBG on the right. Now I can factor 1/2 MP plus MB equals MBG, and you get this pretty unsatisfying MBG, all of that over 1/2 the mass of the pulley plus, nope, I did that wrong. Yeah, plus the mass of the block. All right, and that's our answer for the acceleration of this object. Okay, it's not super satisfying, but that's how we do it, okay? Now, I'm sorry, I just messed up on this last bit. It should be half the mass of the pulley and plus the mass of the block. I'm sorry, I wrote that wrong on the last line of my notes. Okay, so there we go. So that took some time, but I'm going to come back to what we did and why in a minute. Now, once we have A, all right, acceleration is pretty easy. It's just A over R. So I'm going to write, well, what was my formula, my expression for acceleration? The mass of the block times G all over 1/2 mass of the pulley plus the mass of the block. Now I've got to multiply this by R here. So what the book did was M, the mass of the block, over 1/2 the mass of the pulley plus the mass of the block, and then they just pulled out this G over R. It doesn't really matter how you do that, but the point is once you get the acceleration, you just divide it by the radius, and now you have the angular acceleration. Finally, how are we going to find the tension in the rope? Well, we have 2 expressions for tension, don't we? We have this one here, and we also have this one here. Now, I don't know why I decided to do this one, but this is what I did. 1/2 FT equals 1/2 the mass of the pulley, the radius of the pulley times alpha. So I'm going to substitute alpha in here. Ft equals 1/2 the mass of the pulley, the radius of the pulley. Now I'm going to substitute alpha, mb over 1/2 mp plus mb. And then over here, I have my g over r, which is sort of satisfying because now that r can go away. And so what do I get? I get 1/2 mp mb times g, all of that over mb plus half mp. All right, so is that gross? Yes, but the takeaways from here, I hope you're looking to find some parallels between this and what we did in Unit 4, okay? First idea, okay, you're going to write your Newton's second law for the pulley, right? So in a problem like this, you're going to have one pulley and one block. Write your Newton's second law for your pulley. Then write your Newton's second law for the block. For the block, all right? Don't forget, A equals R alpha, or alpha equals AR. You're going to have to use that somehow to bridge that, right? So bridge using FT, okay? That's the general idea for these. We did problems very similar to this back in Unit 4. We've just got stuff that's spinning. So it's tough, but you guys are tougher. You can do this. We'll have some practice, and let me know when you have questions.